Wires and cables. Okay, so this is very important. So when people talk about how big how many gauges your wire is, it's talking about how thick in diameter it is. So the lower the gauge, the thicker it is. See how that's very thin? The diameter is very thin. That's why it's 24 gauge. They're all evens because we're talking about diameter. I'm not sure about that. Regardless, that doesn't matter. Okay. Wire gauges. This is important. It basically tells how big your wire is. The lower the number, the bigger the wire. The smaller the number, the smaller the wire. No, that's reverse. Wait. The lower the number, the bigger your wire. The bigger your number, the smaller the wire. That's gauges right there. Yeah, that's basically diameter size. Solid wire. So there are two different types of wires. Solid wire, it's basically for circuit boards. They're not flexible, and you would use it in projects like these. Do not use it on your robot. Never use this on your robot. Read it if you want. Oh, by the way, you do not use it on a robot because you can bend wires, which can lead to failure over the course of the season. And the last thing you want to do is your robot to fail literally during a match. So don't use solid wires for your robot. Stranded wire. Use this for your robot. Because of its many strands, it is flexible and you can use it for your robot. It's designated by 3 numbers. So it's overall AWG size, number of strands, and AWG size of each strand. So a 22 AWG, that's how thick the whole wire is, has 7 strands of 30 AWG smaller, thinner wires. So let's say if this was 22 AWG 730, this would, the whole width would be 22 AWGs. It would be 7 little wires, and each wire length is 30. Cabling. They're made out of 2 or more separate conductors. Can be side by side, ribbon cable, twisted, bonded, zip cord, or bundled. They use solid strand, braided, insulated, bare, or any combination of wire tables, wire types, and gauges. Yeah, that's cabling. Pretty basic. And like I said, I'm saying it before, I'm gonna say it again. Prototypes, breadboards, custom circuits, solid. Robots, stranded. Do not run your robot with solid wire. That's a big, very big no-no. Terminals and connectors. Spade connectors are used for removal of connections. Some are fully insulated, such as that, and the others are not. Cheap and readily available at hardware big box stores. They're cheap, they're quick, and you can get them nearly anywhere. They're not pretty when crimped, and often break if too much pressure used, but they're cheap, easy, anywhere. These are Anderson power pools. They're crimped on metal conductors designed to snap into plastic housing. I'm pretty sure you'll see this during for your PDP. I'm not sure about that, but I'm 99% sure. And that is available in 10 to 14 AWG, 12 to 16 AWG, and 16 to 22 AWG. Means oftentimes they're pretty big. The plastic housing are available in black, red, green, yellow, white, and blue. And they're high quality insulated connection for wires, but expensive, time consuming to assemble. That is very true. And they can come unplugged and wires loosened if poorly crimped. However, when done right, they are very reliable. XT60, XT60, and 90. XT90 connectors. There you go. So these are require your soldering equipment. I'll talk about that later. They are made from a high temperature nylon with gold spray seam with sockets move. Shape prevents reverse polarity, and when plugged in, the connection is super solid. Connections are already assembled. All you need is wires to be attached. Soldering cup connection for simple analysis and produce great results. So what you gotta do is place the heat shrink away from the heat. Fill one soldering cup with solder. These are the soldering cups, so fill it with solder. You insert the wire into the molten solder, repeat on the other side, and let it cool. Boom, they're stuck. You got it. Great. GG. That's how you do it. Easy. Waggle lever nuts. So, created to be an alternative for wire nuts for easy splicing. Inserted a strip wire and locked in place with a lever. So, insert a strip wire, lock in place with the lever, cut it down, make sure it's locked like that. And most not rated for currents over 40 amps, so be mindful of the ratings. They can be difficult and frustrating with the traditional wire nuts, but lever nuts make splice super easy and result in a secure connection able to handle the rigors of FRC. And lever nuts are also make a good fix if something comes loose at the last minute. And that is section 13, wiring. Sensors and inputs. These are potentiometers and switches. Limit switches. So I'm going to read the TLDR, but feel free to, if you pause and read this if you want to. Motors don't know how to go too far. They tend to hit and break things. So this tells your motor, don't do bad things, then like, I don't know, do something stupid. So hit it, a limit switch, and stop right there, basically. Pneumatic pressure switch, sense air pressure, tells the compressor is shut off before stuff goes boom. Also tells it to turn back on when pressure gets low. These are auto selection switch. They're often in autonomous mode. We need to select different plays based on our alliance partner capabilities. That's like kind of really important. You can use a series of digital inputs and toggle switches, but this eats up DIOS. Often this is accomplished using rotary switches with resistor ladders, like here, and use the analog input to measure which switch position selected. Yeah. Alright, and that is all selection switches. Position switches, sensors. They sense your position. They take the form of a potentiometer attached to a linkage. Usually has 3 wires. VCC, G, and D is single return. Analog, which is basically the information input of the rotor reel, has a 12-bit resolution. 0 to 496 range uses the values to calculate approximate position in space based on the measure return voltage. So that's a resistor mode element, and then you know that's the rotating dial, and now you know where your position is. Encoders, rotary encoders. So basically, it tells you how many times you spin a wheel or motor. And it's actually really important if you have to do like spin it one time. You know how long that takes or how many rotations you have to do. This is the Hall effect. Basically, if you read it if you want to, but this is more you know. So pause the video here. Anyways, we can basically do a lot of stuff, really cool stuff, such as Hall effect sensors. Magnetic fields change the flow of electrons, which we can detect with sensors. This allows us to use magnets and limit switches and encoders. And then this is just saying the brushless motors, they use the Hall effect sensors. Quadrilateral encoders. They count the rotations, but send different signals when going forward and backwards, which makes them more accurate. So, you know, you go this way, that means it's like positive direction, or you go this way, negative direction. Basically goes a forward or backwards direction. More advanced encoder if you like to think that way. SPRX MAG encoders, XPRX MAG encoders, magnetic rotating encoders by CTRE that plugs into the Talon SRX. Supports closed loop operation. Talon SRX can be used for absolute or relative position sensing as well as velocity. Really cool. The encoder senses the magnetic field of a diameter of polarized magnet to determine rational position, 12-bit accuracy, and provides quadrature interface that can be used for relative positioning and a PWM output for absolute position management. This is a closed loop system. Read it if you want to. But I'm moving on. Distance sensors. Ultrasonic sensors. Send sound here. See how long it takes back. Sees the distance. It's like bats. LiDAR. Same thing with the sound sensors, but it shoots a blue laser. Wait, no, it shoots a red laser because these lasers have to be weak. They're not often used just because, like, no, I lied. You won't see it often because they're expensive and there has to be like certain restrictions. Alright, never mind. LiDAR. This is basically like the sound sensors, but it uses lasers to see how long it comes back to measure the distance. That's LiDAR. Position sensors. A gyroscope measures the rate of turn. I hope you know what a gyroscope is. Read it if you want. Magnometer. So this is actually really cool. It's basically a digital compass. It reads absolute measure at direction relative to magnetic north. But the issue is it can have interference from large magnetic fields like the motors, and works best with all of these works best when combined with multiple position sensors. Should not have a robot with just one magnometer and nothing else, no gyroscope or anything. Accelerometer, like your car, tells you how fast you're accelerating. Measure acceleration and vibration in terms of G's. It can be used to detect tilt and detect impacts and make adjustments to the gyro to correct for drift. That's why you use them together, like accelerometer and gyro. You can use them to correct for drift and stuff. Has a 3-axis accelerator and again works best when combined with other stuff. Now, what's in there? This basically tells you what they act and do, some weaknesses, and the bottom. So gyroscope senses turn of the rotation, magnometer acts the compass, accelerator detector change velocity. The inertia measurement unit basically combines of everything you know, the gyroscope, the accelerometer, and the magnometer into one big thing, the inertia measurement unit. It basically allows you to know where your robot is in the physical world and allows for precise navigation. That's why drones usually use it. With the IMU, inertia measurement unit, it's relatively easy to maintain heading even when getting hit by other robots. And the NavX IMU mounts directly on the roadway rail, interfaces via MXP connector, as shown on the right. That's the MXP connector, and there you go. Machine vision and cameras. USB web camera. USB camera. Read it if you like. COT machine vision solution. So you have a Javoy smart machine vision camera, combines a video sensor, quad-core CPU, USB video, and serial port in a very small and inexpensive open source packet. You have Limelight, a design and play smart camera built for first robotic competition. It's for typically for teams with no visual experience or expert mentors. And then you have the Pixie CMU Cam 5. Fast vision sensors designed to simplify learning, can be taught to identify specific objects with relative ease. It requires a coprocessor such as Raspberry Pi, BeagleBone, Arduino, or similar controller. And that is it. So, I hope you guys have learned as much as I have, and I'll see you next time.